This is John Black. But let's talk about these electron withdrawing groups and electron donating groups. Halogens slightly deactivate the ring because they're so electronegative, right? So they are electron withdrawing groups because of their electronegativity. They grab electron density and try to pull it towards themselves, right? And the reason why the benzene is reactive is because of its negativity. If you pull some of its negativity away, you make it less negative, you make it less reactive, right? So when you add a chlorine on here, you don't have to worry as much about adding another chlorine because you have deactivated the ring, but only slightly, okay? Halogens are the weakest deactivators there are, okay? And the reason why they're only slightly deactivate the ring is because halogens have 3 lone pairs, okay? And these lone pairs, electrons, they can donate into the ring through resonance, right? Now, most electron withdrawing groups, like the halogens, are meta-directors, okay? But not halogens. Because of the resonance that they can do with the lone pair electrons, they are orthopara-directors. And I want you to look at this. See down here how you got this is your chlorobenzene. You got your 3 lone pair electrons. What would happen if this jumps over to here and the bond comes down? Then it jumps over here and the bond goes down. Jumps over here and the bond flips back. You keep doing that, you have a resonance. You're taking that electron density and you're distributing it evenly. And look at where the charge is. When you jump your electrons around, look, it goes into the ortho position, pair position, ortho position, and then back onto the chlorine. That's why it's an orthopara director, because these electrons are jumping around on those positions on the ring. That's where the ring is active. That's where it wants to react. And that's why things will attach to those positions, okay? So with this reaction here, with the benzene, making chlorobenzene, you don't have to worry about metachlorination. There is no metachlorination, okay? Because they're not meta-directors. The charge doesn't jump around on the benzene ring on those positions, okay? That all being said, just because it deactivates the ring doesn't mean that the ring cannot add more chlorines to it, okay? I don't know how much it deactivates it, and I'm just guessing about this part here, but I wanted to bring this up, okay? Let's say you add a chlorine to the benzene and it doesn't change reactivity at all. The reactivity of this is the same as this. Let's just pretend, even though it deactivates the ring a little bit. Let's pretend they're even. Once you make 50% of the benzene into chlorine and you have a 50-50 ratio, just statistically speaking, if they react the same, the same strength, you have a 50-50 chance of chlorinating this as much as you do chlorinating this. At that point, what's the point in continuing on? Half of what you make is going to be the double dichlorobenzene instead of putting the chlorine on here. What's the point if half of it is not going to be what you want? Now keep in mind, this is less reactive, so even at a 50-50 ratio, and I'm just guessing on numbers, instead of it going 50% on here, 50% on here, obviously this deactivates the ring, you're going to have a less percentage. Now, I'm just guessing at 30%. Okay, it could be 40%, I don't know. It could be another percentage. But let's just say it's 30%. So, once you have a 50-50 ratio, with these made up numbers, just think about it. 70% is giving you is going on to the benzene, giving you what you want, but 30% is not. So, I mean, just guessing and not looking any information up, if I was to do this experiment, I would only put in enough chlorine to react 50% of the benzene. In other words, the equation says 1 benzene, 1 chlorine, and it'll make chlorobenzene. I would put in 1 mole of benzene, I'd only put in a half a mole of um, chlorine, right? Sure, you're going to only get half of your stuff. You know, you're not going to get all your, you're going to have a lot of benzene left over, but who cares? You can recycle it, distill it, and reuse it in the next experiment, right? Now, like I said, there's no metachlorination. So this would be, if you did have a second chloro group put on, which, you know, it could happen. Look at the, when I was putting the boiling points up, look at the freezing point. The freezing point here, I noticed, is 53.5 degrees Celsius. These are minus 45 Celsius and 5.5 Celsius. So you could recrystallize this out, right? Because it freezes so much earlier. You can take the temperature down to 10 degrees Celsius. The benzene won't freeze out. The chlorobenzene definitely won't freeze out. If you do it slow enough, just like when you recrystallize any solid, right? You want to do it, the slower you do it, the more pure it will be. So you bring it down from room temperature down to 10 degrees C, and this should be able to solidify out, and then you should be able to filter it out, right? This is probably not going to happen because chlorine is a big giant molecule, and the steric interference, I think these ortho positions, you're not going to have much, you know, if any. I don't think you have any that would, but you probably have a trace amount. But this would be your main dichloro benzene impurity, okay, and you can easily get it out, right? The benzene, just redistill it and reuse it. Now this here, they're on meta positions compared to the other chlorines, right? And like I said, there's no meta chlorination. But what happens sometimes, not with chlorine, is you add something to a benzene ring and then you add it again para position. Sometimes you get a rearrangement, okay? Because if you add another one, it's going to be like right here, right? Or right here. You're going to have, they're too close together. And the rearrangement will make it look like this, so that they're all spread out nice and evenly. Even though it's not a meta director, once you get the first one on, you put a second one on it, it can rearrange. When it comes to chlorination of benzene, this does not happen, though. The only way you can get this molecule is through the Sandmeyer reaction, okay? So there's no rearrangement on putting chlorines onto, chloro groups onto benzene. Anyways, the reason why I brought this all up is because it has a lot to do with the way the benzyl chloride is made, okay? Now, the benzyl chloride is opposite. Here, you're deactivating the ring. It's less reactive than this, so you have a good chance of it reacting with the benzene, which you want. But when it comes to benzyl chloride, each time you put a chlorine on here, right, it gets more reactive. So this is more reactive than that, this is more reactive than both of those, and this is more reactive than all of them. And the reason, well, maybe not this one, because you already got it filled up with chlorines. There's no other room for anything else. But the reason why this is more reactive than this is, think about it. You have the same thing as I said with the chlorobenzene. The lone pairs can donate into the ring through resonance. It's the same way with this. If you turn this toluene into a free radical, the electron can jump around and go inside the ring and spread the electron density more evenly. It's more spread out, it's more, that means it's more stable, right? It's like if I'm holding something and I put all the weight on this side of my finger, you know, it's a lot harder to hold it than if I spread the weight out all over my whole hands, you know what I mean? So it's the same thing with electron density, okay? You got positivity here because the chlorine is not only does electron density get donated into the ring, it also gets pulled away by this chlorine, right? Because it's so electronegative. So the next chlorine radical is definitely going to take it. And then when you have two chlorines, now you've got two chlorines pulling electron density and electron density being donated into the ring. This is really going to be positive. You're really going to, the free radical chlorine is really going to want to snag that hydrogen. So now, I've seen instructions, okay, and you can do this. Okay, now you could do this. This is the equation. You can do 1 mole of that, 1 mole of that, and make your product, 1 mole benzyl chloride. And then you distill out the benzyl chloride. Now, the problem with that, and I've seen many instructions, not many, but I've seen a couple instructions, you know, these are in textbooks or whatever, you know, these are written by chemists, and they tell you to do that, you know what I mean? And they tell you, you know, you can weigh up your product, you know, to make sure that you have, if you're doing a mole, you know, figure out how much a mole of chlorine weighs, and weigh your part before and after, and you'll know when you are done chlorinating 1 mole, right? If it weighs as much as 1 mole, then you're done. And you go by temperature also, because the more you have benzyl chloride, the more the temperature will rise, right? Because benzyl chloride has a boiling point of 179, toluene is 111. So the more you make, you're refluxing this stuff, right? Well, once it gets to 179, or, you know, once it gets close up there, you know, you're done. Now, the bad thing about that I don't like is if you do that, okay, let's say you did that and you put in 93% of a mole of chlorine, okay, and then you got 1 mole of toluene, 93% of a mole of chlorine, okay, so it's almost a 1-to-1 ratio. When you get done, these are going to be your figures right here, okay. If you obey this, if you do this method, you end up with 7% of it not being, because we only put in 93%, so 7% didn't react, right? You're going to end up with 55% of what you want, 35% of this, and 3% of this. Now, that's a lot, 35%, and you only get half of it? You only get 55%, 50%? That's crazy. That's not good. Now, look at this. Just like back when I was talking about the chlorobenzene, and I said, only put in half as much chlorine as you need than you're putting in for the benzene. That way you won't overchlorinate, all right? Now look at these percentages. Let's say I put in 46% of the chlorine I needed, okay? 1 mole of toluene and only 46% of a mole of chlorine, right? 45% of it is what you want, and only 1% is benzyl chloride, and none is benzo trichloride, or whatever that's called. You don't get any of that. So why would you do this method where you're putting 1 for 1 mole, and you only get 55%? This one you get 45%. It's almost as much. And you get 0, pretty much, 1% of this. Come on, 1% compared to 35? That's a big difference. And 0 compared to 3? Obviously, you're going to, if it was me, okay, and what I'm going to do is I'm going to put 40%, okay? If I put in 40%, I should get 40% benzyl chloride and 0, or a very small fraction of this, and 0 of that. Yes, I'll have 60%, or in this case 54% of it toluene, but who cares? I can just distill it back out. If it has impurities, so what? I'm going to put it through the same experiment, so it's going to get those impurities back anyway, right? So if you want to make benzyl chloride, that's what you should do. You should only put in 40%, or 45, between 40 and 45% would be my guess, okay? 45%, you're going to get 1% of this. All right. So I would go with 40% and just suck it up, and hopefully you get 0 of this. You know what I mean? You'll have very low of this.